Okay, so welcome everyone to our Marsh monitoring with drones. This is just an introduction. The purpose of this webinar is to talk about some of the great appeal and potential that drones have, but also some of the unforeseen considerations, complications, maybe unanticipated practicalities that we wanted to make known, at least through our speaker's experience. And so for this webinar, we're spanning Maryland and Virginia, which is ancestral lands of many, many tribes. I just wanted to acknowledge being part of Maryland Sea Grant and at the University of Maryland, we are on the ancestral lands of the Piscataway people, and they were our ancestral stewards. And so we acknowledge all the work and stewardship that they have done to ensure that our physical environment is in the condition that we inherited and to help ensure its health and prosperity for future generations. This webinar is the impetus of the Chesapeake Bay Sentinel Site Cooperative, which is hosted out of Sea Grant. This cooperative is a network of land managers, researchers, government agencies who seek to integrate science findings from local observations, such as marshes and observations via drones, across the Chesapeake Bay to improve planning and management decisions regarding sea level rise and ecological changes. Within the cooperative, we have a set working group. This is just a snapshot of some of the partners and agencies represented in that working group, as well as our management team. Within that working group are different people more into their drone work or just starting. And so some of the questions they had or the inspiration for the webinar that we're hosting right now. So we pulled together speakers who are at the crossroads of both marsh monitoring and marsh ecology, as well as drone work. So I'd like to introduce Scott Lergberg, oops, I'm gonna need 1 second here. Scott Lergberg has 18 years of experience as the stewardship coordinator and assistant research scientist at the Chesapeake Bay, Virginia National Estuarine Research Reserve. He helped initiate the NEAR's Marsh Resilience Indices project and was the site lead for multiple reserve efforts. Scott has extensive experience in wetland biomonitoring and serves as the CB NEAR Virginia's GIS coordinator. He, with Alex Demeo, Alex is the field and lab specialist and is an FAA Part 107 certified drone operator. He has taken several training courses in collecting and processing drone imagery and is the drone operations lead for the CB NEAR in Virginia, as well as other programs at Virginia's Institute of Marine Sciences. Ben Malmgren is the master's student at the University of Maryland Center of Environmental Science Warm Point Lab. He works with Dr. Cindy Palinkas and Dr. Lori Staver on using drones to enhance vegetation and coastal morphology monitoring of living shorelines. Dr. Cheryl Doughty is an assistant research scientist at NASA Goddard and the University of Maryland's Essex Center. She uses remote sensing to study how coastal wetlands are responding to climate change from CM scales measured with drones and across the globe with satellite imagery. We have Kory Angstadt, who is a field technician at the Center of Coastal Resource Management at the Virginia Institute of Marine Science for the last 20 years and has been a UAS pilot for the past 7 years. He uses drones and GIS technology to study shoreline systems, assess wetland plant communities, and create high-resolution elevation maps. Annalise, Kenney, and I are both from Maryland Sea Grant. Annalise is the Assistant Director for Communications at Maryland Sea Grant, and I am the Coastal Resilience Coordinator, as well as the coordinator for the Chesapeake Bay Sentinel Site Cooperative. All right, so Scott and Alex are going to begin our webinar talking about how to purchase a drone and different platforms and applications relevant to purchasing that drone. We'll then move to Ben, who will talk about the related data sets and sensors that are necessary in addition to the drone that you purchase. Cheryl will talk about all the considerations and parameters for your first flight, and then Kory will talk about post-flight processing. And while we hope that this is a super informative webinar, we realize that talking to one another might be the most informative experience. And so we've made an effort to start a community of practice story map that Annalise is going to preview. And then we're going to open it up for questions and answers. So with that, these are the things we're going to talk about. And I am ready to pass it to Scott and Alex.
I'll go ahead and get started. Taryn, if you could go to the next slide for us. So I'm going to start by talking about drone use considerations. When getting involved in purchasing a drone, there's several cost considerations. The drone itself has a cost associated with it. So you can either start out with a very entry-level drone. They cost around $1,500, and you can end up in the high-end drones that go upwards of $20,000. So initial cost buy-in is something to think about. With that, sensors, as we'll go into more detail about them later, but sensor costs, again, starting on your entry-level drones, they predominantly are built in with the drone purchase. And as you move into your higher-end drones, you can have multiple sensors that you're able to change out, each with their associated cost. So your drone and sensors are the initial first cost you need to think about. Moving forward, you'll need to be able to process and potentially program your flights out. So you have software costs to consider, whether you're going to be using a processing software that Kory's going to talk about later, or a pre-flight software. Some are given out for free, and others do have a cost, either a yearly subscription or an upfront expense. Training is also something we do consider. A lot of the drones do come with training if you buy the higher end ones, but some of the vendors do charge for training. They will usually do it on site for you. And there's also training involved in post-processing. Using the post-processing software, there's a lot of training classes offered for that. And then computer costs, there's most of the software you're going to use for post-processing, your standard computer cannot handle it. So you may need to consider upgrading your computer system. The higher end drones fly off of laptops potentially or tablets. So there's a startup cost there. And you may also have to think about storing all this data. If you don't have a server network available to you, or perhaps you want to go cloud-based, that's all considerations that you need to have when starting in the purchasing of your drone. And the next is, what type of drone do I need for the work I'm doing? There are two main drones. There's fixed wings, and fixed wings are a stable platform that offer various types of sensors that you can add to them. They can cover large areas at a time with limited battery changes. You can go up to probably 60 to 90-minute flight time on one. They usually can handle stronger winds than a quadcopter. Transportation is something to consider of them. They are quite larger, some of them being in large cases or a hard case. So transporting them to the field sites is something you have to consider. Usually they minimal amount of flight operations or controls. So as an operator with a fixed wing drone, you potentially are just going to set up an autopilot situation, and you will have a control stick in an emergency situation, but you are not going to fly that drone. Usually you're going to let the autopilot software handle that. So mid-flight changes are very limited in that situation with one, which is just something to consider for how you're going to fly and what your ultimate goal is. And then most fixed wing drones also, the camera points straight down. So you are only getting a nadir flight with one. With a quadcopter, they offer smaller and lightweight options all the way to a large option that is capable of carrying a heavy payload. You may have less flight time on a smaller quadcopter drone, as the one in the image here, or you may be able to get larger flight times with, or longer flight times with the larger options out there. They're able to hover, and most of them also offer a constant video feed. So while you're flying them, you can actually get a live feed of what the camera's showing you. Cameras are also usually mounted on a gimbal and completely adjustable during flight operations. And then also you can go into what sensors do I need. They offer LiDAR sensors for ground truthing. They offer high resolution cameras for doing either still images, video images, or orthomosaics. And then they also offer multispectral cameras to get into your different wavelengths of light reflecting back. And we'll talk a little bit more of these later on. Next slide, please. These are two of the quadcopters that NIRS currently operates. The Mavic 2 Pro has a maximum flight time of about 30 minutes. It can travel 18 kilometers away from its location. With that being said, though, FAA regulation does require us keep it in line of sight at all times. Its maximum wind speed that it can handle is 29 kilometers per hour, although we do not ever really fly in that high winds. We like to stay in the 10 to 15 mile an hour wind speeds tops. It has a 3-axis gimbal with it and a live feed camera. These are really great if you need to do some outreach work where you want to get a little video. Maybe you guys are doing some field work. The live video feed of it shows you what you're taking a picture of, what you're taking a video of, and it's a really high quality camera for its price. It's about $1,500 to get into one of these. It's a complete workhorse for us. 90% of the time when we go in the field, we take this with us. It'll fold up, goes right in a backpack. So we may not use it that day, but at least we have it with us. You can fly it off of your cell phone or a small tablet. So everybody's got a cell phone nowadays. You don't need to consider buying a tablet, extra computer, or anything like that. This one we use a lot to do quick sight checks as well as the video outreach. And it can also be programmed to do grid flights. So we do use this for orthomosaic flights when our takeoff and landing sites may be restricted for a fixed wing operation, or a really small site where a fixed wing just is a little overkill for the job that day. The Matrice 350, as you see on the bottom, we are just getting into this drone. We just recently acquired it. It'll be a tool for us. We got it with a multi-spec camera, a 10-band. So we're going to be using it to look at vegetation habitats and vegetation health, as well as branching into tracking harmful algal blooms with drones versus just boats in the water. It offers a maximum flight time of about 55 minutes. Again, max distance for this is 20 kilometers away from the controller, but FAA requires that you keep it in line of sight at all times. Max wind speed with this one is 43 kilometers per hour. Again, something I will probably never test. We like to stay in that safe realm of 10 to 15 miles an hour, but having a higher wind speed capability is good. If the wind does change on you, you know you can at least get it back in safely. This one also offers interchangeable sensors. So we currently have the multi-spec camera for it, but it is capable of carrying a LiDAR module or an RGB camera for standard video photography. When using the multi-spec on this, it will not have a live feed from the camera. So you are flying a quadcopter either via autopilot or by joystick. So on the front, it does have a forward-facing camera so that you can see where you're flying and the obstacles, and that will live feed to the controller. You go next slide, Taryn. This is the fixed wing operations. This one is the current one that NIRS operates. This is the EBX. It is a hand-launched fixed wing drone. You can see that I am launching it there. You throw it up in the air. It weighs about 3.5 pounds with its camera on board and batteries. Its wingspan is 38 inches and it's made of a foam construction with a little bit of carbon fiber on the skid plate for landing. This one does tie into a RTK system, so we're able to reduce ground control targets with and still have a very high accuracy with each image as it's geolocated. Max flight time is about 60 minutes with proper wind with this drone. So a large increase in flight time, we're able to cover a much larger area for observations. The radio link with this one is 1.9 miles. Again, you have to keep it within line of sight. So we don't ever test how far it can go, but we've had no issues with it. Wind speed is up to 45 kilometers an hour. Again, we tend to fly this one. We will fly in a little bit higher winds, but we tend to try and stay under 20-mile-an-hour winds with this. And the accuracy that we're getting, our resolution in our photos is about 3 centimeters on the horizontal, and the clarity is 0.9 inches per pixel. This one is a workhorse for us in our orthomosaic imagery. And we are currently working on expanding it into multispectral work. So we're going to start using it for vegetation habitat. Some things to consider with this drone is it is a vertical, or it is a throw to launch, as you can see in the image, and it also is a linear landing. So when it comes into land, it lands very similar to an airplane where it will skid on the ground. So your landing and takeoff space, you do need to consider. And there's also no live feed camera on this. So you fly it via the laptop. When it's up in the air, you have no idea what images are taking or if they're clear. So that is something to consider with purchasing a drone like this. Next slide, please, Taryn. This is two options if you are going to go into the fixed wing. These are both vertical takeoff options. The first one is the Trinity F90 Plus. The propellers that you see on it will rotate up and it will take off much like a helicopter. And then they will rotate down and it will fly as a fixed wing. So with that, you get the perks of the takeoff of a quadcopter, but you get the flights of a fixed wing. It offers about 90 minutes of flight time, several payload options as well. And in the image, you can see that they are running a multispectral camera in that little white bay of the photo of it on the beach. And that module can just change out. So you can fly several sensors in one day. The other option is the Wingtra, which is the orange drone in the corner. That is also a vertical takeoff drone. The perks are that they require about 15 feet of takeoff and landing space, where a linear landing fixed wing takes about 100 feet of takeoff and landing space. So these give you the perk of a fixed wing in the space requirements of a quadcopter. They are both NDAA compliant, which is something we'll talk about a little bit later. That is due to the new government regulations. So great option for those working in the federal level. Both offer multiple sensors, and they both also have full autopilot flight with the option of stick landing. So you could use a controller to land it and take off, but it is advised to use autopilot when flying your missions. Next slide, please, Taryn. So some operational limitations that we have to think about. Takeoff and landing areas are always your biggest restriction. Where am I taking off? Where am I landing? Who owns the land that I'm taking off and landing? Do I need permits to take off and land there? Am I in any type of airspace restrictions? The map we have up here shows all the zones in red are restricted airspace. So you cannot operate a drone over those sites, and you cannot take off or land in them. So that's a consideration where you're flying. Is that going to be a problem for you? Also, space requirements. As we said before, with a fixed wing linear landing drone, you need 100 feet to 150 feet for landing and takeoff, preferably with no trees in the area. Then how much space, and then a quadcopter or a VTOL fixed wing you need about 15 feet of space. We have FAA restrictions that we have to consider. We have no fly zones. The FAA does control a lot of airspace near airports, hospitals. So we have to look at our maps, make sure we're flying in proper airspace and that we're not interfering with any type of commercial or manned aircraft. Drone requirements. The FAA requires certain things with drones. You have to have them registered with the FAA. There are weight restrictions for basically amateur pilots as we would be considered with them. And they also require times that we're allowed to fly. So you have to fly during daylight. And if you want to fly beyond that, you have to get a special waiver through the FAA. Weather considerations as well. We have to consider the wind speed of the day and whether that wind speed will change to a higher rate that we're not comfortable when planning. We have to think about wind directions, especially with fixed wings in terms of them taking off and landing. Is there rain in the forecast? We have to think about if it's a light drizzle, you will probably be okay to fly. But if you get a heavier rain, your drone may be able to handle the rain, but it is going to corrupt your images. So there's really no point in flying that day. So weather plays a big part. And then depending on where you're flying, whether it's overcast or sunny, does affect the quality of your images that come out. We also have agency restrictions to consider. Specific agencies that you're flying for may have specific restrictions. For example, is the federal government is starting to restrict manufacturers of drones. They have to be NDAA compliant. That's a newer rule that's hit the market or hit the drone world. So everybody is still trying to fully interpret that, but most FAA flights, FAA funded projects will require an NDAA compliant drone. NOAA, if you're going to fly for them, also has restrictions as well. We have to consider endangered species through the Endangered Species Act. We have to be aware of migratory birds and not disturb them, as well as things as simple as butterfly habitat. We have to consider where that is and where our flight operations occur to minimize or have no disturbance to those species. I'm going to hand it over to Scott at this time.
Hey, everybody. I think my colleague might have gone a little long, so I'm going to move through these really quickly. So I was going to talk about some of the applications. So for the Mavic, for example, that we use that a lot for helping our shoreline studies group at VIMS here with their Living Shorelines project. So, for example, on the upper right of this slide is the Captain Sinclair Public Access Authority site. This was a site that won some awards from the American Shore and Beach Preservation Association. So we were flying this site for communications post-restoration. The bottom right corner is Packet Farm. This is part of a project to accelerate the scale and rate of living shoreline implementation in Virginia. So this was flown to help provide obliques and overheads for design work. And then in the bottom left is a site of the East River in Matthews, Virginia. And this was flown post-construction when you can see there's some rock sills and some natrix oyster restoration to assess performance of the site. So next slide, Taryn. And then we're just getting involved in a project through the NEARS Science Collaborative. It's a funding source through the NEARS. It's called this is called Drone the NEARS, but it was based on a Drone the Swamp project that was done in the Southeast. And this was basically trying to use drones as sort of an intermediate source between satellites and plot-based vegetation monitoring. There's issues with plot-based monitoring in wetlands that you miss, like you see A there, corner A, you miss die-off events, or you can cause disturbance at the site. But if you use satellites for mapping wetland habitats, you often have insufficient resolution, or you can have cloud cover. So the question is whether we can use drones to bridge that gap. If you go next slide, and so we'll be using our Matrice 350 with a multispectral camera for this project. But in that Southeast project, they looked at linking drone imagery to ground survey parameters, including elevation, canopy height, ecotones, percent cover, and biomass. And they've developed some standard operating protocols. We'll be testing those protocols in two of our different habitats. We'll be trying it in the tidal freshwater habitat, which is novel for the project, as well as trying it with our fixed wing drone. So next slide. And then finally, as a near, one of our big responsibilities is to map our habitats on timescales. And so we have 4 reserve components which span the York River estuary, going from Sweet Hall Marsh, tidal freshwater, down to Goodwin Islands at the mouth of the York. If you go to the next slide, please. So we used to have to rely on BG imagery for the mapping products, but in 2017, we had an opportunity for NGS's remote sensing division to come down with their staff and fly our Sweet Hall site with their EB Plus at the time. And that was a really great experience for us. It kind of showed the utility of the fixed wing drone and how we could use it in our mapping efforts, being able to map tide control, being able to map on clear days, and being able to map annually. So based on that experience with the NGS remote sensing division, we went ahead. Alex got certified. We have purchased 2 different EB drones, fixed wing drones, since that time. If you go to the next slide. So now we're using them at our sites. We've been able to develop products like this upper right at Goodwin Islands is a really high resolution habitat map with 15 different descriptors, habitat descriptors at Goodwin Islands. And really when you're looking at sea level impacts and looking at those small scale changes in your habitats, having this level of mapping product is really important. And then in the bottom right, we've also been able to map shorelines consistently and develop products like change analysis. So we can look at shoreline change on decades as well as annually. We can look at pond development and forest retreat. So that's just some of the applications we've used in our program. And I want to move on to Ben.
Good afternoon, everyone. Again, my name is Ben Malmgren. I'm a master's student at the UMC's Horn Point Lab. And today I'll be discussing with you all some of the common data types and sensors that we see in Marsh monitoring. Next slide, please, Taryn. So this is something that Scott and Alex touched on briefly, but it is important to consider while we're exploring our sensor options, what I call the 5 Ps. And firstly, our first P being your project goals. So what exactly are you trying to observe? What's your management objective? What successes have there been as far as monitoring these types of phenomena with the sensor you're curious about? Secondly is product quality. So what sensor specifications, flight parameters, settings, etc., do you need in order to produce the quality results that you're looking for? Thirdly, you need to consider price. So what all is attainable given your budget? Fourthly is payload. Like mentioned, some sensors come pre-integrated into your airframe. Others need to be mounted independently. So when you do mount a sensor like that, are there any impacts on the operation of your drone that you need to consider? And lastly is your processing workflow. So what all goes into, whether it's time, knowledge, additional software, et cetera, to move from your raw data collection to your final outputs. Next slide, please. Next slide. The first sensor we'll explore is the optical RGB. This is your most standard camera. It works in capturing imagery across the visible spectrum of light, that RGB meaning red, green, blue. And so this is a common sensor we see across entry-level platforms all the way up to professional grade systems. Comparatively, these sensors produce very high resolution images, which makes them incredibly versatile in that these data can be processed into 2-dimensional and 3-dimensional output. Some examples of that we see are very high resolution site mapping in the form of orthomosaic. In the exploring 3-dimensionality, we can see data types processed into digital surface models or terrain models, useful for exploring coastal morphology, whether that's geomorphology or extending to vegetation monitoring in the form of extracting canopy height. And there's been work taking that a step further and from canopy height, estimating above ground biomass. So a sensor with a lot of range, but also limitations. So again, we're only working within that visible spectra. And with a passive sensor like this, one that only collects data on what it can immediately see, we can be limited in our data collection abilities. An example of that is how vegetation density can obscure terrain below and affect your elevation model product. Next slide, please. Multispectral imagery and sensors expand upon RGB in that they enhance the spectral range. Pictured below is a MicaSense Red Edge MX. You can see it has 5 lenses there. Those are all sensitive to different bands of light, whether it's red, green, blue. And this sensor specifically extends to both red edge and near infrared spectra. This is significant in that a sensor like this can be used to calculate different indices, or essentially ratios of reflectance of light. A notable one being NDVI, or the Normalized Difference Vegetation Index. This is a very common index in remote sensing for essentially measuring plant greenness. So we see it applied in a lot of vegetation monitoring contexts. Some work that I'm personally involved in using multispectral imagery includes assessing vegetation percent cover. There's been work done for classifying species specifically, as well as above ground biomass, land cover classifications, example being shoreline delineation. So it really expands the types of processes that are attainable with remotely sensed drone imagery. That does come with its consequences. As you're collecting more data, your file sizes increase. So that's important in both storage and processing. These sensors also typically produce a lower pixel resolution than your optical RGB imagery, and they're also more expensive. Next slide, please. I'd like to mention LiDAR, which stands for light detection and ranging. And this system is very useful for creating 3-dimensional models where the sensor itself is active by emitting laser pulses, and it measures the time it takes for that signal to return to the sensor and the intensity of that return to then recreate a 3-dimensional environment. So this is very useful for 3D mapping of both features and landscape. A benefit this has over traditional RGB optical imagery is that it's better able to penetrate through the vegetation canopy. So you may have a more accurate and informed understanding of your spatial environment. We're able to generate these very dense point clouds. And unlike those passive sensors, this active sensor is able to collect data regardless of lighting conditions. So we see a sensor like this common in topographical monitoring, things like coastal morphology, and again, vegetation monitoring, extracting canopy heights. Really, it's something where you get what you pay for, and a system like this is, although very beneficial, it's a lot more expensive than traditional RGB imagery and the photogrammetry process. So next slide, please. And we'll touch quickly on thermal or infrared sensors. So these function by detecting heat radiation. We see examples in Marsh context for determining habitat use and performing specimen counts, very commonly with nesting birds. This reduces potentially the physical intrusion into the marsh, expands the number of organisms we might be able to detect. But these sensors do come with their drawbacks. These thermal cameras are pretty low resolution. They're quite expensive and limited in their use, unlike some of the other sensors and data types that we've explored. Next slide, please. So lastly, I want to touch on some ongoing work that myself and my advisors, Cindy Palinkis and Lori Staver, are involved in. And that is expanding living shoreline monitoring with multispectral and RGB drone imagery. Next slide, please. Here's an example of a recently constructed living shoreline in just outside of West Ocean City, Maryland, where we've went and performed transect-based quadrat vegetation assessments, where we estimated visual percent cover within each of these quadrats, and then conducted a drone flight where we captured multispectral imagery. From that imagery, we're able to generate that NDVI. And from there, based on those NDVI values, we created a classifier which classified pixels as either vegetated or non-vegetated, and then paired those drone-derived estimates with our field estimates. And quickly you can see in lower instances of vegetation cover, we see a stronger agreement among these two methods. However, as our field observations, our observed coverage increases, we find that our drone-derived estimates typically overestimate that vegetation coverage. And we're looking into methods for reducing these false positives and incorporating more parameters into our classifier. Next slide, please. Here's some optical RGB imagery at work for another living shoreline recently constructed in Maryland, where we generated a digital surface model, or essentially an elevation map, and compared that to measurements recorded with an RTK during an RTK survey across this site. And so those red boxes delineate instances where we see also varied land cover. Comparatively, we have a very sparsely vegetated shoreline running up to a developed upland forest region. And so very quickly, we can point out that when all data are compared against each other there, we see a much lower agreement between the two methods, as the data within those tree canopies, we're not able to get return signals from off of the floor beneath, which leads to an overestimation of elevation. And so as those highly vegetated portions of this site are removed, we see a much stronger agreement between our digital surface model and our RTK observed observation. So this just goes to show the importance of understanding the context with which your sensor is most functional in. Next slide, please. Thank you.
All right. Hey, everyone. My name is Cheryl Doughty. I am an assistant research scientist at NASA Goddard and funded through UMD ESSEC. And I admittedly have gained a lot of drone experience not in this region, but I'm really excited to be here now and be involved with you all. Next slide. So Scott, Alex, and Ben set this up all very nicely. I think the key message here in selecting your equipment is really the drones and sensors you select should be catered to your research questions and get you the data that you need. And again, considering site selection in terms of permitting and who your partners are on the ground is really important in determining where we can fly. The best place to start looking to see where you can fly is the FAA and get yourself certified. And again, before you go, always very important to consider the weather predictions. And next slide. And also getting an idea of the flight and field study design to get you the data that you need. So say, for example, you want to compare your drone imagery to satellite data, for example, Landsat at 30 meters. You might just want to check out what that looks like so you know where to go and collect your samples and fly your flight. Next slide. And the reason that's important is because, as Scott mentioned, some of what we're collecting on the ground and what we want to compare it to, say, for example, Landsat, we might not really be capturing all the variability that we see on the ground when we go out there. And that's really where UAVs and drones can help. Next slide. So I have a lot of experience flying the DJI Matrice 100 equipped with a MicaSense Red Edge. You've been hearing a lot about this so far. This is really a specialized camera that has 2 extra bands in the Red Edge and NAR that really allows us to say something and learn about the vegetation, the wetland vegetation on the ground. And again, this is a type of quadcopter. It's small. It's a little bit more customizable compared to something like an off-the-shelf DJI, or something very customizable like this DJI Matrice equipped with a hyperspectral camera, which falls under the expertise of Tom Bell. So if you're interested in hyperspectral stuff, you can look at his work. Next slide. And so again, in planning your flight, there's a lot of different software options, commercial versus open source. Some are off the shelf that come with your drone. Others are, again, more customizable. I, for example, have used the DJI Go, which is now outdated. So this is a very fast moving field and you have to try to stay on top of the technologies as best you can. No matter what your software you're using, some of the most important flight parameters you'll be setting are the altitude, the speed, and the imagery overlap at which you fly. And this really determines the battery power that you're going to need to cover your study area. And in your study area, you can set the bounds in your flight planning software. You might be able to upload a shapefile. I have always been told to, change the direction of the flight lines and to always start furthest away from you and have your drone be on the return. And this is because if you have any sort of hazards or errors occur with your equipment, you kind of want to get your drone back as fast as possible. And again, this is really all about optimizing your battery use. So when you get to your field, it's also, or considering your field site, also consider, the tides, the lighting conditions, the surrounding areas. Are there going to be people around? As my colleagues have said, is there anywhere that we can or cannot fly? So next slide, a lot of what I'll be showing you in setting up your first flight is this case study from Carpinteria Salt Marsh, where I did a lot of my PhD work, so admittedly SoCal. But here we use drones to map seasonal biomass in a drowning salt marsh. So we got high resolution imagery from our drone at about 6 centimeters. And again, that mica sense allowed us to calculate these vegetation indices to say something about our vegetation. And then we can compare those to the field collections of biomass we make on the ground to develop these models to scale biomass up to our entire site. And we can do this across a couple of seasons. So some potential of what drones can do for us. Next slide. So in going out and doing your flights, I always suggest having a checklist. So make sure you have all of your equipment you need. Everything needs to be charged. Again, depending on the equipment you select, this list could be very different. You'll likely have a GPS. As we mentioned, some RTK GPSs are really great for getting centimeter accuracies, and some other UAV equipment that might be helpful for your specific sensor. So something like calibration panels, GCPs, which we've heard are ground control points, tarps, things like that. And then once you're in the field, again, doing your surveys and setting up this home base. So home base is your ground control station where you and your drone begin and end together, hopefully. And then you can collect your imagery and your samples. So next slide, trying to go through this very fast. And again, I love a checklist. This is really helpful as you're starting off flying a drone in any site. So again, kind of doing your initial check of the area. And then physically, checking the physical aspects of your drone. Is it clean? Is it working? Is nothing broken? Making sure your radio and your ground control systems are talking to each other, whether your ground control is your phone, an iPad, the controller that came with your drone. You want to make sure they're talking to the drone. Again, doing any sort of sensor calibration before you fly, and then doing your aircraft systems check. So turning it on, is it all ready to go? Is it giving you the green light? And then taking off. So we've heard a lot about flying your drone, and in a lot of the software we have now, it makes it really easy to press go and it'll kind of automatically take off and land for you. So this is one option. Next slide. But I was also taught to be prepared to manually land and take off your drone. So be prepared to do that. And one of the reasons for this is when you call your drone home, it's relying on its own internal GPS system. And depending on how good or bad that may be, you may or may not miss your home base. So be prepared to do that, and then shutting down. And again, this list was developed through the guidance from UC's unmanned drone policy. You really should check with your institutions for the most up-to-date guidance. And again, a list is great. Commercial airline pilots do this every time they fly us somewhere. It's a good way to make sure you're doing your due diligence. Next slide. And so here's an example of what a ground control station looks like. It's not always pretty, but home is where the drone is, and you just want to make sure it can stay clean and land safely. Next slide. Here are some examples of those calibration panels specific to the work I did with the mica sensor. And so these images show you the output images from each of the bands in the mica sense, which is pretty cool. Same thing for the spectral on white balance and diffuse reflectance targets. So these types of calibration panels will help you correct for differences in your lighting and your imagery. Next slide. An example of ground control points. So these are designed to help you reduce the geolocation errors in your resulting imagery. And so they can be bought or made, but you just need to make sure you see them in your imagery. And the next slide shows an example of a poorly sized and flight height to see your GCPs. And Kory will talk about why this is important, but we can move to the next slide. Here's a good example of how you want your ground control points to be placed across the site, kind of evenly dispersed and spanning your site. If you go to the next slide, you'll see, and here's an example of some of the RTK stations nearby that allow us to get at those centimeter accuracies in our drone images locations. Next slide will then show you what not to do in the field. So here the GCPs are all in the middle of our site. That's going to give you bad geolocation errors on the right and the left of your image. But
unfortunately, it seems like Cheryl cut out. Since we are crunched for time, I'm going to continue to potentially advance the slides and hope that Cheryl comes back momentarily. As you can tell, Cheryl has done extensive work in some very cool environments. So I'm sure she would be very happy to describe her work more. But again, unfortunately, I'm not sure what happened to her. And in the interest of time, we are going to pass it over to Kory, who will talk about briefly the post-processing of when you finally get your drone back to your office, your computer. So take it away, Kory.
All right, thanks. Yeah, I'll try to go through this pretty quickly so we can get this over with. So what do you do once you get back into the office and you have all these pictures? Let me share my screen. So you have a whole bunch of pictures like this drone flight that I did. This particular flight had about 900 images. They're, all geolocated, but what do we use to get them all into an orthomosaic or in a digital elevation model? And so I use mainly Agisoft, Metashape. It's a program that was developed in Russia, so you're not allowed to buy it anymore since the Ukraine war. So there's another program out there called Pix4D, and I'll show you that. They basically do the same thing. They take images, stitch them together. You can make 3D models, whatever you want out of them. So you bring your pictures in. It has them all geo-referenced. You can see the angle that I had the gimbal at during this flight. I typically, for an orthomosaic flight, I fly with a 70-degree angle on my gimbal just to get some elevations. Once you get your images in there, you can bring in your ground control points. And this area, I was only interested in this one shoreline. So I have the GCPs spread out about on the northern side of this marsh. Then what the program does is it creates tide points underneath from the imagery. And so you start getting all these points that the program picks out from the imagery, and it starts creating an image that you can kind of tell what's going on. So this is the whale tail marsh that we go to. There's going to be an oyster aquaculture float system out here. So we're going to keep an eye on if it helps with erosion of this marsh or anything. So that's why we're flying this marsh. So after you get your tide points and your ground control points all set in, you can create a dense point cloud, and now you're getting even better resolution. And these are all points. These are not, this is not an image really, it's just points. They each have an elevation, they each have, you know, different parameters. So you can then take that point cloud, create a mesh that smooths out everything, and then you can go on to your orthomosaic. Let me bring up an orthomosaic. So this is the orthomosaic that you can then export into ArcGIS, and you can also do digital elevation models. So you can see that in this marsh, some of the higher vegetation is black needle rush, lower, of course, alterniflora, and then back towards the forest off to the left here, we have some Phragmites, and then into the maritime forest. Let me bring up Pix4D real quick, just so you can see what that looks like. All right, so Pix4D is basically the same thing. You got your pictures, create tide points, create a dense point cloud, and triangle meshes, and you can export mosaics and DSMs. So what do you do with that after you have all that information? You then bring it into Arc. Let me share that. So here, so we have an ArcGIS program. We can bring in orthomosaics in. You can start making polygons around the vegetation. The resolution is really good, so you can really get in there and see the edges of the communities. If you fly low enough, this was a 100-meter flight. If you fly low enough, you can start seeing periwinkles and oysters and mussels and stuff. So if you're doing biological surveys, you can see that. You can also bring in your elevation models, and that's your DSMs. If you're flying multi-spec, you can bring in NDVIs, the indices, whether it's the normalized vegetation index or water index or whatever indice you want to bring in, you can bring that into ARC. And then also the point cloud can be brought in just like a LiDAR system, and you can create 3D imagery from that point cloud. So that was really quick and dirty, but we're running short on time. So I think Taryn's going to have my email. If anybody has any questions about anything, you can send me an email and I can answer it. So I think that's it.
Thank you so much, Kory. Yes, when we started planning the webinar, all of our speakers emphasized how each topic could be an hour, and that has seemingly become apparent. I'm going to quickly pass it to Annalise to highlight how you can get in touch with all of our speakers.
Thanks, Taryn, and thanks everybody here today. This has been amazing. I'm Annalise Kenney. I lead communications for Maryland Sea Grant, and I just wanted to take a few minutes today to introduce a partner initiative with this drone monitoring webinar. This is the Marsh Monitoring with Drones story map. And so as our team has been working to present all this information about how one gets started using drones in monitoring projects, we thought it would be also helpful to create a resource highlighting projects from around the Chesapeake Bay region. So we have a draft story map coming together that we hope to fill with all the information about all of the exciting projects going on. So I'll just take a few seconds to share that with you. So here is the draft story map. It's pretty straightforward with some pins for each of our projects. Some of the projects that were presented here today, for example, you can zoom in and kind of check out project descriptions. some of the pilot interests and their certifications, and of course, contacts. So this is a resource just to hopefully loop everybody in together. You can reach out to people in your region or just see what's going on. And down at the very bottom here, here's my pitch to take a quick survey to have your own work featured in this resource. So I will drop a link into the chat to a survey you can take, and it's a quick survey. Fill out your information and we will put you into the story map. Feel free to share around. So I'll share it in the chat and throw it back to Taryn.
Thank you so much. So yeah, the goal is that we just highlighted, 4 different speakers who are doing drone work, and we know that is not the extent of all the cool projects that are happening. There, we tried to cross-section both Marsh and drone, but there's certainly heavier drone-focused operations throughout the Chesapeake, such as we certainly have a drone lab out of the University of Maryland too. So I am going to very selfishly ask the first questions of you all, just a few quick poll questions, and then understandably, for those of you who can't stay past 2 o'clock, thank you for joining us. But if anybody is willing to stay on and ask any questions, I hope our speakers will entertain those. So I am navigating quickly to the polls. The first poll is a really simple one. It's whether you would be interested in participating in the story map or not. So please take 2 seconds to do that for us quickly, so that I can try to follow up if you would like to be added to the map as a way for people to know about your projects and perhaps network and collaborate or learn from one another. I'll give it just a final 5 seconds to do that. Thank you. Next, this is an introduction, and we're certainly willing to fill a space if there are future topics that you would like to learn more about. And so if any of these components of today's webinar is something that you'd like more detail on, please indicate your interest now. I'll just give this another 15 seconds. So if you haven't made your selections, please do so. All right, final 5 seconds. And I'll end this poll too. At a glance, you guys realize that Cheryl and Kory didn't have perhaps as much time as they could have to explain all their things. So the highest interest was in design and post-processing. My final slide is just if you would want to engage in ways other than webinars, such as learning from folks who are doing drones and just to talk to one another. You can click on networking if you want to get out into the field. Sea Grant and the cooperative would potentially explore ways to do that. So any other indications for those who are choosing other and have specific ideas, please put them in the chat and we'll do our best to be responsive to your preferences. I'll give this another 15 seconds. We are over time, so thank you for everyone who's sticking on. And then I'm going to close it out in 3, 2, 1. And we have a fair distribution, but networking is certainly of interest, so we can try to facilitate that, and the story map might be a great place to start. All right, those are my questions for you. If anybody would like to raise their hand or ask a question in the chat, we will do our best to address those. And thanks again for tuning in this hour. It was a full hour, and so yeah, it looks like we have a question in the chat related to Ben's talk. Can you expand a little bit on how you achieve the pixel classification for your NDVI data? Are there any tools available to do this?
Yeah, absolutely. First off, thanks for your question, Alec. So the way that we determined the pixel classification for the NDVI data that I showed you there, it was based on essentially selecting a threshold value for the NDVI within that range. NDVI is runs from values from -1 to +1, and values lower on this scale tend to be less associated with green vegetation, and values higher are more likely to be green. So we ran several, essentially determined multiple cutoff points throughout the NDVI value. For that data that I showed you specifically, we had a threshold value of 0.27. So anything above 0.27 on that NDVI scale was considered and classified as a vegetated pixel, and anything less than that was not. As far as tools available for doing that, I don't know off the top of my head. And if you find any, let me know, because that took a long time to do. So yeah, as far as I know.
Thanks, Ben. We had another few questions come in. I don't think towards anyone specifically, but one was, are your DSMs consistent between flights over the same locations as in different dates?
Well, for when we're just using RGB to create the digital surface models, it can change with the vegetation getting taller throughout the growing season and not. So that can change your DSM elevations quite a bit with RGB, but if you're using LiDAR, in some cases you can minimize that because that will punch through most of the vegetation. It's a little bit tough in tidal marshes because a lot of the grasses are laying over on top of each other, so the lasers don't always get through. But yeah, they're fairly consistent from year to year, I would say, at the same growing season.
There was another request in the chat that Cheryl addressed, but I'll note it. Suggestions on open source apps to flight planning. Ryan is using Map Pilot Pro, but says it's clunky, and that the Before You Fly app is already retired. And it looks like, Cheryl, if you wanted to chime in on your suggestion to that.
Yeah, so again, kind of shows you how quickly things become outdated. So now when you go on to the FAA Before You Fly website, they have a bunch of apps suggested. So definitely always start by checking the FAA. And I'm trying to remember what I just tried to use for an open source app, but unfortunately, it also wasn't that great. And most of my experience has also been using the AggieSoft Metashape, which is also no longer advised to use. So does anyone else have any suggestions for open source?
Pix4D capture for flight planning is free. It's only available on a few drones. A lot of the newer DJI drones are not compatible with it, but some of the older ones are, and we've used that in the past for our Mavics and our some of our Phantoms that we fly. For the most part, though, the newer DJI drones that we get, which we're going to have to move away from that, but they have their own proprietary flight software on them. So Pix4D is what I use in a pinch if the drone is compatible with it.
I'm also a Pix4D capture user.
Since we are significantly over time, I think we'll try to wrap things up unless anybody wants to slide in the 11th hour final minute with one final question or comment. All right, well, we really appreciate the turnout today, and thank you for giving your input where perhaps we go next. And we will hopefully post this recording as a resource to everyone, and I can additionally send out the speakers' emails for anybody who wants to follow up individually. Thanks again, everyone, and have a great rest of your day.